Okay, hello. I'm going to talk to you about quiz corrections. Go over some of these items on the quiz. I'm not giving you any answers, just things to consider and things to talk about. Number one, if you need to make a correction on number one, just identify that this is, we're taking the antiderivative of sine and cosine. So some marks that I might want to look at is try to remember what the antiderivative of sine is and what is the antiderivative of cosine. So have a reference sheet available in case you need it now. The antiderivative of sine would be, let's see, if I take the derivative of cosine, I get negative sine. So if I take the derivative, the antiderivative of sine, I'll get negative cosine. And if I take the antiderivative of cosine, I will get just regular sine. Okay, so the signs are important there, where negative cosine and positive sine for each one of these. So now when I do this, I'm just looking at, okay, I have to take the antiderivative of sine. That's going to give me negative cosine. So just think about that as going to be negative 4 cosine x. Let me undo that. Okay. So think about that, sine is going to turn into negative cosine. And then this cosine is going to turn into, let's see, just regular old sine. We can keep that negative 5 on the front there. And now this plus 6, just remember that if you ever take the integral of a constant, what we're really doing is we're adding a power and then dividing by a power. But what that's going to be is just basically 6t. Right, think about taking derivatives, right? When you take the derivative of 6t, it goes down to 6. So if I take the antiderivative, right, that's obviously going to go from 6 back to 6t. And we would call this plus c dt here, right? Anytime that we're taking the antiderivative without numbers, we're going to add in that plus c there. So just remember that that 6 turns into 6t, right? It's not going to disappear. You'd be doing the derivative if you do that. And then, of course, look at those reference sheets there. Okay, let's clear that. Let's go on to number 2. Number 2, antiderivative, right? Once again, this tells me that we're doing the antiderivative. If you need to remember the antiderivative or the anti-power rule, that's the opposite of our derivative, the opposite of the power rule. So this is how it works. If I have something, if I integrate x to the n, that's going to be equal to, basically, we're just going to subtract 1, add 1 to whatever that power is. Or we're going the opposite order, right? So instead of subtracting, we're going to add an exponent, and then we're going to divide by that same exact new exponent. So whereas the derivative, so I'm going to stamp this over here, this is the antiderivative. Remember that the derivative goes the other way. So, right, if I took the derivative of x to the third, then I bring that to the front and subtract, this goes the opposite direction, right? So basically adding a power to make that 3 and then dividing by 3 is going to be the antiderivative over here, okay? That's what we're doing. So in this case, I have x to the third. We're not doing the derivative. We're not doing the power rule. We're doing the anti-power rule. So what I need to see you do here is actually take this, and for each one of these, let's add a power and then divide by a power. Power is 1, so if I add a power and then divide by a power. So that's what this turns into. And then we're going to evaluate on 0 to 4. And when I do this, remember that when we do this, we plug in the 4 and the 0. Okay, we're going to do upper minus lower. So instead of having x's in each one of those cases, we put parentheses there. I'm going to put in that 4. So plug in my 4 to start. And then I'm going to subtract the same thing when I plug in a 0. Right? And this is the math that you need to do, right? I took this function. Let me grab a new color here just so I can highlight some things. I took this function right here, and I just basically replaced the x with a 2 in each case. Or sorry, the x with a 4 here, and then I replace the x with a 0 here. So it's the same exact function as up above. I just replaced it with those variables, those constant numbers, right? So everything else stays the same, 4 and 0, and notice how I'm always going to subtract those two values. All right, so you go ahead and do that work. Just follow your order of operations. Do these two first, then I would do these two, okay, because really what we're doing is I should have parentheses in there. All right, and then you're going to subtract those two numbers. Go ahead and give that a try. Let's go on to number 3. Number 3 is a Riemann sum. Okay, so when I do a Riemann sum, what I need to do is I need to basically break this down into rectangles. We're always going to find our width is going to be our change in x of our rectangles. So from -2 to 0, that's a width of 2. From 0 to 4, that rectangle has a width of 4. And from 4 to 5, that has a width of 1. So the width of those rectangles changing, and now we're going to find the area of each rectangle according to, well, let's see. It says talk about Riemann sum from -2. That's how I knew to go from -2 to 5. Sorry, I should have read that first. Using a left Riemann sum. So for each one of these, 2, 4, and 1, I'm going to choose the height that is associated with the left side of that rectangle. So I'm going to do 2 times 6, 4 times 4, and 1 times 7. And since we're finding the area underneath a curve, we're going to find those 3 areas, and we're going to add them up. That's going to be your answer. Okay, so Riemann sum is width times height. I knew the 6, 4, and 7 because it was a left Riemann sum. Area, 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 bang. Next. This one, I know a lot of us maybe got a little tripped up on. It gives us a lead-in. The function f of x and g of x are continuous on this interval. Okay, that's typically the case. And we have 3 integrals here. From 0 to 5, f of x, the area is 3. 0 to 2, g of x, that area is 10. And from 2 to 5, g of x, that area is 5. And what we want to know is the area from 0 to 5 of g of x. Let's highlight some things. That we're only talking about g of x here. There and there. We don't care about what's happening to f of x. Now, neither one of this tells us what's happening from 0 to 5, but I have one that's telling us from 0 to 2 and from 2 to 5. So if you think about a graph here, I don't know, from 0 to 2, we have some curve. Looks something like that, let's say. I don't know, I'm making something up. And then from 2 to, let's say, 5, our curve f of x, or g of x, whatever that is, maybe looks like that. I don't know, okay? What I'm doing here is I'm just drawing an example of how you might interpret this. I wouldn't expect you to sketch it, but just why this makes sense. From 0 to 2 of that curve, the area is 10. Should have chose a different color. I'll circle that 10. Now, the area from 2 to 5 of g of x is 5. So this is asking us, what's the area from 0 to 5? Well, let's see. I got 10 from 0 to 2 and 5 from 2 to 5. So that whole area is 15. Okay, now how can I get that? I'm just seeing that it's going from 0 to 2 and from 2 to 5. Okay, so if I think about that, basically this whole thing from 0 to 2 then 2 to 5 is the same as 0 to 5. Right? So I basically can just take those two areas and add them together. Bang, 15, done. Let's look at the next one. Now for this next one, you really got to be careful with what you need. I'm not going to tell you anything about the answers, but just how you would get them. We've got this, Sarah's playing pickup basketball. I got this situation. She runs up and down the court with the velocity given by such. V of t is in meters per second and t is in seconds at t equals 0. Sarah's position is 5 meters. I'm asking why I underlined that and nothing else. We got a lot of key information in here. We want to know the acceleration. Well, one thing that I need to underline here is that we are given velocity. So remember that when we go from position to velocity to acceleration, if we're going in that direction, we got to take the derivative. Well, we're not going from position to velocity, but we are going from velocity to acceleration. So we need to take the derivative of this to get our acceleration formula down here. Now I'm going to label this A of t equals. So now how do I take the derivative? You have to use the power rule. Remember what the power rule is. It's for derivatives. If you're given something, right, and you need to take the derivative, we're going to move the n to the front, and then we're going to subtract 1 from it, right? That's the derivative. Okay. So make sure that you're doing that. Also, 2 is a constant. So I'm going to tell you right now that the derivative of a constant is 0. So this 2 right here, when I take the derivative, is going to give me a plus 0. So take the derivative of 8t squared by moving the 2 down and subtracting 1. And then once again, since 2 is a constant, that's going to be plus 0. You find out what that derivative is going to be right here. That's going to be your acceleration equation. Now, when we find that, we can actually use that now to find our acceleration. Great. And then finally, what is Sarah's distance traveled? Now, this is where we've got to think. We are given, we have velocity formulas and acceleration formulas, but we need distance. Distance is a form of position, where she is, how far she's gone, not how fast, or not how fast she's increasing. So we can basically just go from velocity back to position, which means the antiderivative. Okay, so I got to take the integral from 0 to 3 of 9t squared plus 2. And if you're stuck on how to do that, remember that this is the antiderivative. And I talked about this on the very first problem and the very second problem with how do we do the antiderivative. Go back to problem 2 to figure out how I do the antiderivative. Now, the only thing I would say is you're going to do your antiderivative, like add a power and divide by a power, add a power and divide by a power. But instead of saying plus c this time, they actually give us what the c is. So you're going to take the antiderivative of each one of those. And then at a time of 0, position is 5. So our starting point is plus 5. So take those two antiderivatives and then just make sure that you plug in 3 and 0. When you plug in 3, that should give you your answer. Because if you plug in 0, well, actually, no, you do need to plug in 0. Because that's going to give you something different here. It's probably going to give you 5. All right, so plug in 3 to each one of these. Get your answer, plug in 0 to each one. Get your answer, and then just make sure to subtract those. That's how we do the antiderivative with those. Give that a try. Reach out if you have questions, but that was just some thoughts in order to kind of get you started.